So today we'll be doing the 2008 exam. So this one's pretty old, so there is probably going to be some stuff that's different. I also don't think you guys have gotten to some stuff that's covered on this exam, but since the final is literally like in a couple weeks, I'm just going to go ahead and cover it so you guys can look back at it later. I'll try to make sure to point out everything that won't be covered on the third exam. But if I miss anything, just make sure you're checking with what Dr. Bean has officially posted um, on that page, which is on her website now. So yeah. So we're almost through with all of our nomenclature. So I put this table back on here for you guys. So for exam 3, you're gonna have to know kind of all of these functional group nomenclatures except for amines. Amides you will have to know, but amines I don't think you guys have learned it. You guys haven't done chapter 19. And then this is also organized by priority. So it's good to remember the priority because occasionally she throws you a question where there's two functional groups that you'll have to choose between. So it's good to have that in the back of your mind. So let's just go ahead and get started. All right, so for this first nomenclature, I like to identify what the kind of functional group is going to be. So in this one, I see that I have an amide right here. So for amides, the nomenclature is going to be like alk and amide. And so that's going to be, this part is the alk and amide part. And then the groups that are attached to the nitrogen are going to be substituents with this one. And so for substituents on nitrogens, so this is for amides and amines, they're a little bit funny because we don't use numbers to describe them. We actually use the letter N, but we'll get to that in a second. So just identifying my parent, again, we have our alkane amide. So I'm just going to go ahead and start on that side. So we're going to start numbering our first carbon as the carbonyl, and then we're just going to go to the right. So 2, 3, 4, 5, 6. So I have a hexane base. That's eventually going to become a hexane amide, but we do also have this double bond in there that we need to pay attention to. So our double bond starts at carbon 2, so we are going to have hex 2-ene, or you could do 2-hexene, and then again, with that functional group, it's going to be converted into the amide name, so that's going to become hex 2-ene amide, or amide. Yeah, so it could be 2-hexenamide, either way. I just always did it this way, so. So that's going to be our parent name. And so again, for amides, the nitrogen groups are going to be subs in a way. So we're just going to go ahead and go to our substituents. So we have a methyl on a nitrogen, and we have a methyl that's on just the regular alkyl chain. So we'll still have a dimethyl. And again, the way you denote the positions, you would do N for the one that's on the nitrogen. And then the other methyl is at carbon 3 on that main chain, so it's just going to be N3 dimethyl. So it'd be kind of like having like a 3,5 dimethyl, or like a 3,6 or a 3,3. It's just that anytime that you have a substituent coming off of a amine group or an amide group, it's going to be N instead of a number. And that tells us that it's coming off of that nitrogen. I don't know off the top of my head. I've always put N first, and it's N first. That's what sounds right to me. I've always done N first, so maybe it got ingrained in my mind just to do that. Other than the methyls, we have a benzene right here. So remember from our chapter or exam 2, we have benzyl and we have phenyl. So make sure you remember difference. This one, since it's coming directly off of that nitrogen, there's not a CH2 in between. It's going to be a phenyl. So again, that's on a nitrogen, so it's just going to be N-phenyl. We don't have any more substituents that we have to worry about, so we can just look at our stereochemistry. So we do have stereo at that double bond, so we'll just go ahead and do the priorities for that. So over here at carbon 2, we're looking at a hydrogen versus a carbonyl, so the carbonyl is going to get our priority. And then on the other side at carbon 3, we're looking at a methyl group versus a CH2, CH2, CH3. So CHH wins over a HHH. And so that means our stars are on opposite sides of that double bond, so that means our stereo is going to be E. And since there's only one stereo center, we don't have to put the number. In fact, I don't think you would get credit if you put the number. It's just going to be E. We don't want to be redundant. And so now we have everything that we need to put it together. So we just put our stereo at the front. We have E, and then again, we always put our substituents in alphabetical priority, not including the number prefixes. So M comes before P. So we are going to have N3-dimethyl and phenyl. And then our parent name was either 2-hexenamide or hex-2-enamide, depending on your preference. Any questions on this one? Yeah, you should get credit for that. Okay, I'm gonna go ahead and move on. All right, so for this next nomenclature, this time I see that we have an ester. So again, just make sure you're familiar with all the different names. So for esters, we're gonna do our O8 ending is our parent name. So we have our parent, we have our subs. All right, so for esters, again, carbonyl is always going to be 1, and then I'll do it in a different color. The carbon coming off of that ester oxygen would also be 1. So the main name is, the O8 name is going to be coming from that longer portion from the carbonyl again. Change my color back so I'm consistent. So this is going to get our O8 name on the left side. And then on the right side, with that ester part, that's going to be kind of at the front of the name. So one thing that's different about some of these new nomenclatures is that we have like spaces now. We kind of have pieces of the name that we have to put together. And so esters are one of these functional groups. We're going to have kind of two pieces. We're going to have the ester part, and that will be whatever alkyl, and then our parent would be the alkene O8, and those two are separated by a space. So just make sure you're very careful when you're writing out your nomenclature. For our parent, again, just number down that chain. So we have a 7-carbon chain, so that's a heptane base. We don't have any double bonds or anything to worry about, so this one is just going to become heptan, and then O8 is our ester ending. I'm going to call this, I'm going to give this a separate little category right here, because it's not technically a sub, so I want to distinguish that. So for our alkyl part, again, we just start at the carbon that's connected to that ester oxygen, or the single bonded oxygen. So we have a 4-carbon chain, so that's a butane base. And then we have a double bond at carbon 3. So that's going to become but3-ene or 3-butene. And then because it's not the main chain, it's kind of that first little piece, it's going to get that YL ending. So this is going to become but3-ene and then eel. And so again, I'm putting this one kind of in its separate little category over here because it's not technically a substituent. It is going to be separated by a space at the beginning. So yeah, we don't have any substituents on that alkyl chain, so we can go back to our main chain for our substituents. We have this OH group. So remember that alcohols become hydroxys when they're substituents. And that's starting at carbon 4. So we have 4-hydroxy. And that's all the subs we have for that, for the whole thing. And then for our stereochemistry, we do not have stereochemistry on that double bond on the end because it has 2 hydrogens on that carbon 4, so we can't distinguish between the two. But we do have stereochemistry for this chiral center here at the alcohol position. So oxygen is going to get our highest number. Hydrogen is going to get our lowest number, and so then we're between these two carbon groups. So just starting at the next one over, so we have CH2 versus CH2, that's the same. CH2 versus CH2, that's the same. CH3 versus a carbonyl, so that carbonyl is going to win. So going towards the right is going to be my higher priority, and the left would be my lower priority. So if we do our number, we go 1 to 2 to 3. We get R as our stereo. Our lowest priority is on A dash, so we're good to go. We don't need to change that. And then again, we just have that one stereo center, so we don't need to put a number or anything like that. Okay, so now I have to put it all together. And so again, these new nomenclatures are a little bit different than what we've done in the past. So for our esters, again, we kind of have two pieces. We have the alkyl, and then we kind of have the parent O8 name. So we're just going to start by putting that alkyl portion first. So we have but3-ene-il. And then this is kind of where it gets a little bit funky. So that stereo center was on that parent segment, I guess. So we're actually going to put that at the beginning of that second half of our nomenclature name. It's not going to go at the very, very beginning. It's going to go at the beginning of the side it belongs to, I guess. So we put our stereo after our alkyl name, and then we just put everything else together like we normally would. So we had a 4-hydroxy, and then our parent name was just heptan O8. And that is the name for this one. Any questions? No. Moving on to our last nomenclature. So this one is going to be an anhydride. So whenever you're doing your nomenclature, be very careful this time because some of these can look pretty similar. So like esters can look similar to anhydrides. Sometimes she throws on like little tricky ones where you might have an ester and then like just an extra carbon away is another ketone, but that's not an anhydride. An anhydride is specifically when they're kind of holding hands. The carbonyls are holding hands. But anyways, so this one's going to be an anhydride name because of this little structure we got going on. And so for anhydrides, they're also going to be one of those names that has spaces between them. And so for anhydride specifically, we're going to go with our alphabet priority for those two pieces. So we're going to have our A piece, B piece, anhydride. So for example, ethyl, methyl, anhydride, or something like that. The E goes first, so it gets the front, and then the next one would be the methyl, and then anhydride at the end. So our parent, I'm just going to put anhydride. Okay. And so then this part is going to be 1/2, and this part is going to be our other half. All right. So starting with this left half, again, our carbonyl is going to be our number 1 carbon, and we're just going to go down the chain from there. All right, so we have a octane piece. So I'm just going to label this as kind of my octane piece so I know what I'm talking about. All right, so I have my octane base. I don't have any other double bonds or anything else like that. I do have a substituent with that nitrile. And so, again, this is when it's really useful to remember your ranking. There is a nitrile in there, but anhydride does come before, or I guess it has a higher priority than nitrile. So if you had done the nitrile as your parent name, you would have gotten probably the whole thing wrong. So make sure you know your priorities. And then for nitriles, whenever they are substituents, they are considered cyano groups. And then that cyano group on our octane piece is coming off of carbon 4. That's going to be 4-cyano. We don't have any stereochemistry on that half, so we can just go ahead and move on to the other half. And so this one's a little bit tricky. Anhydrides are pretty tricky, especially if they're like this. But we technically have a carbon and then a benzene. So this is going to be classified as a benzyl group. And that's the whole piece. So I'm just going to put benzyl. No stereochemistry, no other substituents. So that's kind of just the whole piece. And then whenever we have our anhydride name, our pieces become the oic names. So octane would become octanoic. And then our benzyl would become benzoic. And yeah, that's all we need to put this one together. So again, for our pieces, we're going to put the alphabet priority first. So we have our benzoic, starts with a B, so it goes first. And then we have a space. And then we have our left piece over here. And that was a 4-cyano octanoic. And then at the very end, this is our parent name, anhydride. Okay. Questions on that one? Alphabetical, yep. Yeah, space. For most of these new ones, you're going to put spaces. I think amides are kind of the one that you don't do that with. Nitriles, I don't think you do that with either. But yeah, like esters and hydrides, yeah. Maybe it's just those two, actually. But yeah, you would have to do the space. You can't do like dashes or... And you might want to be careful about how you write it, too, in case the TA is like, oh, well, you didn't put a space there, so... Yeah. Because we have to account for the carbonyl carbon too. So we're kind of considering that as like the CH2 and then benzene. So yeah, it's a little bit funky for anhydrides. Anhydrides are not that common. Most of the time it's amides, esters, nitriles. But this is 2008 and they were tougher back then. So, well. Yeah, I'm gonna go ahead and move on for sake of time. Moving into the facts section. Okay, so just starting off with this first one, we have reactivity with H2O. So it's going to be very helpful to know your reactions for this exam because some of it kind of bleeds over into our fact section. So for this question, what it's essentially asking you is we need to find the most stable leaving group. So if you remember your amide reactions, whenever we react an amide with H2O, either in the form of H3O plus or our base NaOH. We form a carboxylic acid, and we have like our amine portion off to the side. So whenever we react these compounds with H2O, we're going to do the same thing. So we would form like a little methyl. We'd have our carboxylic acid, and then our amine would come off, and so we would have our little anion there. So we need to look at the stability of these leaving groups, and so we want, in this case, we want withdrawing groups to spread out that negative charge. We want withdrawing groups. So if we look at all of these, we see that the carbonyl part is all the same, so we can kind of ignore that. The difference is in the amide part. So on the left, we don't really have anything on that benzene. In the middle, we have a nitro group, and so we know that nitro groups are strongly withdrawing. And then on the right, we have an OH, and we know that OHs are donating groups. And so again, we're trying to stabilize that leaving group, and so we want to have withdrawing groups to spread the negative charge out as much as possible. So again, we want our withdrawing groups, and so that nitro compound in the middle is going to be our most stable and therefore our fastest rate. So it's going to get our number 3. And then between the left and the left doesn't really have anything, it's kind of just neutral. But the right has a donating group, and so a donating group would destabilize that that leaving group and that negative charge. So that's going to have our slowest rate. And then the left, that one's just going to get our middle position. Questions on that one? Okay. For our next facts question, we're being asked about pKa. So for pKa tells us kind of how acidic a compound can be. So a low pKa actually means a stronger acid, and a high pKa would mean the opposite, a weaker acid. So this is kind of like an acidity question. I mean, it pretty much is an acidity question. So for each of these, we need to identify our acid, and we need to deprotonate it. So for all of these, that's going to be that carboxylic acid there. And so kind of similar to the question that we just looked at above, we form this anion, and so we want to try and stabilize that anion as much as possible to increase the stability and therefore increase the acidity and lower the pKa. So this one's almost like a reverse scored question. So we see that our benzenes have different substituents. On the left, we have an aldehyde, and so that carbonyl aldehyde is going to be a withdrawing group. In the middle, we have a amide, and so this amide can be donating, but it can also be withdrawing because that nitrogen is going to be kind of caught up 50-50 between donating towards the benzene and then also trying to resonate with its own carbonyl. So this one's kind of like 50-50. And then on the right, we have just a pure amine. So it's just got its lone pair. And so this one, kind of like an OH, it's just going to be fully donating. And so now we can identify which one's going to be our most stable acid, our strongest acid, and then rank the pKa's. So since the group on the left was just a full withdrawing group, this is going to be our strongest acid. And so therefore our lowest pKa. So again, this is kind of like a reverse scored question. So even though it's our strongest acid, it's going to be getting our 1 because it asks us to rank our lowest acid as 1. In the middle, we had that 50-50 group. So this one is going to be kind of donating, kind of withdrawing, so kind of in between on acidity. So it's going to get our number 2. And then on the right, we had just a full donating group that would be destabilizing that anion. And so this one is going to be our weakest acid, and so highest pKa. So make sure you're really reading these questions carefully because it could be pretty tricky. Yeah. Mm-hmm. Yeah. I know she has like that chart in the notes, so if you just memorize that, you should be good. It's just kind of like explaining it. So I just like to say 50-50 because I feel like it's the easiest way, I feel like, for me to think about it. But okay, moving on. For number 3, for some reason we were asked another PK question twice in a row. A little weird. But rank in order of increasing pKa. So just keep in mind what we just talked about. Strongest acid is actually going to get our number 1. However, this is kind of talking about our chapter 22 stuff here. So we have all these carbonyls, these esters, aldehydes, and stuff. And so we don't actually have like an OH or anything that we can deprotonate to be a really good acid. But all these carbonyls do produce acidic alpha hydrogens. However, remember that an aldehyde proton is not going to be a good, it's not going to be a very acidic hydrogen to take off. So we're kind of going to be ignoring those aldehyde hydrogens, and we're going to want to go for the protons that are kind of in the middle of these carbonyl structures. So we find our anion positions. I'm just going to draw in our anions here. In this middle one, it's pretty straightforward. This one on the right is, I don't know, it's a little bit more difficult to think about because we're not actually between 2 carbonyls directly. But just remember that we want to form the most stable anion possible. So I'm going to choose this one right here because that anion would allow me to resonate with that carbonyl. Whereas if I had chosen this position here, I actually can't resonate with that oxygen. And that oxygen can't resonate with me because we've all got our octets already. So we have all our anions. So again, we just need to look at the stability of these. So ideally we want more resonance or more withdrawing groups. So we'll just go ahead and take a look at that. So on the left, we can resonate with that carbonyl on the left, and we can resonate with the carbonyl on the right. Just keep in mind, though, that this ester will be kind of competing for that resonance just a little bit. In the middle, we have 2 aldehydes. Can resonate with either one. On the right, we only have one resonance structure. The carbon on our right is just a regular CH2. Again, it's got its octet, so we can't do any resonance with it. So since the group on the right, the compound on the right, only has one resonance structure, that's going to automatically make it a worse acid because it does not have additional stabilizing factors. So more resonance is always better for when you're trying to be a stable anion. So this group on the right, it's going to be our worst acid. And so therefore, again, remember we're kind of like reverse scoring here. It's going to have our highest pKa. Okay. So now just between the left and the middle. So this one's a little bit tricky. Both of them have 2 resonance contributors. They're both pretty decent. We got, they would form our O minuses. However, remember that the group on the left, that ester oxygen is going to be kind of competing for that resonance. And it's going to be kind of donating its electrons towards the carbonyl via that resonance. So that's actually going to make this one slightly not as good for an acid. I'm just going to say competing, not as good. So the group on the left is going to be in our middle position, and then our best acid, the lowest pKa, is going to be this 2-aldehyde structure because it's got 2 resonance structures, and both of them are fully for that carbanion. We're not competing with a ester oxygen or anything like that. I don't know, not really. I mean, the symmetry. Yeah, it's more of the fact that the ester oxygen would be donating and destabilizing that negative charge versus like symmetry. Another structure with 2 alpha. You mean like something like this?
Yeah.
For a question like that, I feel like it would have to be either like symmetrical or something like that. I don't know if she would give you one like, I don't know, if something like that, but I don't know. I guess for this one, like, I guess maybe this one might be slightly better because it doesn't have that additional methyl group that's donating by induction, but I don't think you would get that tricky of a question. I don't know. Okay. I'm gonna go ahead and move on, for time's sake. For our last question, we have a decarboxylation question. So honestly, if you get one of these questions, you better know it because it's like one of the easiest facts questions you could get. So for decarboxylation, that's going to be where we have our carbon dioxide leave. And so the way that happens is we need a beta keto ester, or we need like a beta dicarboxylic acid. We basically need a carboxylic acid or an ester that's beta to another carbonyl. So for our Greek letter nomenclature, we're going to look at our first carbonyl, and in this case, I'm going to start at our ketone, because the ketone is not going to be the one that's leaving. The carboxylic acid might be the one that's leaving, so I want to start with our ketone. So I'm going to have that one be 0, I guess. I don't remember what the official letter for it is, but I like to say it's 0. So then our next carbon out from that position would be alpha. So if we go to the left, we have an alpha position. We go to the right, we have an alpha position. In this case, we don't really care about the right side, so I'm just going to ignore it for now. And then going to that carboxylic acid down at the bottom, my beta position is going to be that carbonyl of that carboxylic acid. So this would be my beta position right here. And so for decarboxylation, we want our ketone or our 2 esters or 2 carboxylic acids, we want them to be beta to each other. So since this carboxylic acid is beta to that ketone, this would be able to undergo decarboxylation. So we're going to put yes in the box. This next one, in this case, we have 2 carboxylic acids, so it doesn't really matter which one I choose. I'm just going to say that one's going to be my starting point. Our alpha carbon is here. And then again, our beta carbon lands on the carbonyl of that second ester or carboxylic acid or whatever. So this one would also be a yes. For this last one, again, we have 2 carboxylic acids. I'm just going to pick one. That's my starting point. So my next position is alpha. Next position is beta. And then next position is gamma. So the carbonyl of my second ester, carboxylic acid, whatever, is not in the beta position, so this one cannot undergo decarboxylation. And so the reason why we just need these to be in the beta position is because of just the interaction between the groups. We need them to be close enough to actually perform that decarboxylation reaction. It's kind of like a little concerted mechanism. Everybody's kind of doing something all at once, so we need them to be close by. Any questions on that one? Okay, all right, going on to our reactions. Again, just a disclaimer, there might be some stuff on here that you guys haven't covered. I'll try to make sure to point out the stuff that you guys won't have on exam 3, but I'm still going to cover it so you guys can look at it for the final. So for this first reaction, we have a carboxylic acid and we have an amine. So we have a primary amine. And so this is going to form an amide. And since our our amine is just NH3, it's just going to become a primary amine, NH2, in that first reaction. So the second reaction, this one is a little bit special. So this one is unique to primary amides. It would only work with a primary amide, not like a secondary or a tertiary amide. And so this is, it's kind of like a dehydration mechanism, sort of, not really. But what this one does is it actually turns our amide into a nitrile. So we go from that amide to the nitrile. For our last reaction, we have LaLH4, then H3O+. And so this one is just going to be our strong reducing agent. And so for nitriles, this one is just going to reduce it fully to the CH2 NH2. So back to a primary amine. Any questions on the first? Yeah, so POCl3, it could also be SOCl2. So if you see one of those with a primary amide, then it would do this nitrile formation. I think POCl5 too, or I think I might be thinking of PCl5 from Earth. Okay, going on to the next set. So these ones are fun, the retrosynthesis ones. So typically, not every single time, but typically if you see two carbonyls, a ketone, usually it's a ketone and an aldehyde, typically you're going to be doing your hemiacetal formation. So we have our little structure here. You could also write it out like this. And so this is going to be like our little protecting group. And so typically you see these when you have a ketone and an aldehyde because this is a selective reaction. And so it will selectively protect aldehydes because they are faster at reacting with that compound. So step 1, I have my little, like, I don't know, it looks like a little face. And see that we need to attach a CH3CH2 onto our, to get to our end product. So for this next one, I know that I have a carbonyl. I need to attach a group and I eventually form an alcohol at that position. So that seems pretty much like the classic Grignard reaction. So since I'm adding a CH3CH2, I'm going to have that be my Grignard part. And when that reacts with our little structure, we'd have our O-, we'd have our new 2 carbon piece attached on there. And then for step 3, I can do my H3O+, and that will simultaneously turn that O- into the OH, and it will deprotect that aldehyde and turn it back into the, or deprotect that hemiacetal and turn it back into the aldehyde. We're not done yet because we do need to get to this carboxylic acid at the end. So again, make sure you're paying very close attention. So for this last step, I need to use an oxidizing reagent that turns the aldehyde into the carboxylic acid, but does not affect my alcohol. And so a reagent that you can use to do this is your silver oxide and water. And so this is it's a pretty mild oxidizing reagent, and it selectively will oxidize your aldehyde and turn it into that carboxylic acid without affecting your alcohol. If you were to use Jones or sodium dichromate, those would be too harsh. Actually, I don't know, because this is a tertiary. It specifically uses this one in the key though, so I'd probably lean towards that one. Any questions on that set? You mean 3 and 4 combined, kind of? I'm honestly not sure. I've only really seen it as H2O, so. She does mention, okay, she does say in the notes you could use Jones, or in the key you could use Jones, or sodium dichromate. She does say best for the silver one, but if you can't remember it, then it's fine. Okay, so this next reaction is a chapter 19, sort of. I think it is in chapter 22, but with the way she jumps back and forth, I don't know what is covered and what is not, so bear with me. So this series is technically what's called stork synthesis. So that is in your chapter 22 notes. Can't remember what page, so don't ask. But yeah. So this first reaction, if you're just looking at this first reaction by itself, this specifically is a chapter 19 reaction. And so whenever we have a secondary or tertiary amine, so we have a amine with 2 little methyl groups on it, and we have a carbonyl, this is going to form an ene amine. So it's called an enamine because you attach your amine and you form a double bond. So ene-amine. There's also the imine synthesis, but that's when you have a primary amine with a carbonyl. So that's similar, but not the same thing. All right, so step 2. Again, this is overall a stork synthesis, so if you want to look at that, it's in chapter 22. But what happens in step 2 is we have this partially positive carbon. It's very partially positive because of the electronegativity difference between the double bond oxygen and that chlorine. And so our double bond can actually act as a base to attack that carbonyl. It's kind of helped out by the nitrogen pushing towards that double bond. Double bond goes and attacks that carbonyl. The carbonyl gets turned into the O minus, and then that gets reformed to kick out that good leaving group chlorine. So it's kind of a lot going on. But you don't have to show all this, you can just show the product. In the key, she separates it, so I think you would need to. I think for this one, she does want to show that intermediate. And so that intermediate that we form, we've attached our little carbonyl group, our little ketone. Now, again, that nitrogen was kind of helping out in donating its lone pair. And now it's going to be not partially, it's going to be fully positive. So this is kind of like an intermediate sort of step. And then for step 3, it kind of just fixes, I don't really know what to say. It fixes the N+, and this actually turns the nitrogen into a ketone. to kind of go back to our little aldehyde. So this is kind of a way of getting like a dicarbonyl compound in a slightly different way than some of the other chapter 22 stuff. Were you going to say something? Yes. Okay. All right. All right. Number 4. So for this one, this is some chapter 22 stuff. So we have our NaOET. We have this dicarbonyl compound, our beta keto ester. So we are going to first deprotonate that position in the middle, that alpha hydrogen. All right, for our next step, we have a alkyl halide. So this, we have our anion can attack and kind of steal that alkyl group for itself. I'm just gonna, not the best drawing ever, but it's okay. And then we have our OET group. And then for step 3, so this is the decarboxylation reaction. So what happens is there's this whole kind of concerted mechanism, but basically we're just going to cut this whole ester off, including the carbonyl. That whole thing will leave as a carbon dioxide. So that gives us our ketone and our, I think I'm missing, yeah. Good enough. So that gives us our ketone and that alkyl group added on. Yeah, if there's an ester, H3O plus and 180, it's going to be decarboxylation. Usually it's the beta keto ester too, so. Okay, I'm going to go ahead and move on. Okay, so for this next one, it's kind of like another retrosynthesis. So I think this one is also not going to be covered on exam 3. I think this is Claisen. So Dr. Bean told me that y'all weren't going to be covering Claisen for this exam, but again, I'll just do it for your final. So we have formed a beta keto ester. And so Claisen is really good at making beta keto esters. So for Claisen, we start with an ester, and it usually like kind of attacks itself, and stuff gets kicked out. So our so we have our ester right here. For our first step, we do the NaOET. We get our anion. And you don't have to draw this, I'm just kind of showing. And so then for Claisen, what happens is you can either have another, a different ester react, or you can have the same ester react. So this would attack that carbonyl. Carbonyl gets kicked up into the O minus, comes back down, kicks out that good leaving group OET, and that's how we get our end product. So we've got that ketone, and then we just kind of attach the rest of our group there. So for this one, the whole answer is just going to be this little dude in the box. So that's Claisen. I don't, it's not, it doesn't do this part where it attacks itself. It kind of does stuff at the end to, I don't, I'm gonna be real, I don't remember the mechanism right now. And what you said. And again, this plays in, it's not gonna be on exam 3, but for your final. So, number 6, all right, so we have an anhydride. So anhydrides react a little bit weird. So for this one, whenever we have an amine with an anhydride, one side is going to kind of attach to the amine, and the other side is going to get turned into the carboxylic acid. This top one, I'm just going to turn into my amine. So it's going to become NH and then CH2, CH3. The bottom side is going to be my carboxylic acid. And then we have that isopropyl group. So this is separate. It's not connected. So I'll just draw it a little bit better. So that's step 1. Step 2, we have our step 2 and 3 is our strong reducing agent LiAlH4. And so this one is going to, step 2 and 3 are together. This one's going to fully reduce both that amide and the carboxylic acid. However, it does it slightly differently. So for amides, what happens is we actually fully reduce the carbonyl to a CH2. So we're just going to turn that into an amine. And then on the bottom, this we know our carboxylic acid will just get turned into a primary alcohol. So LaLH4 with our amides is a little bit different, but for the carboxylic acid, it kind of does the same thing. Yes, 2 and 3 you can combine on this one. Okay. I'm going to go ahead and speed this up because I'm on 25%. Yeah, it turned into the CH2, NH, CH2, C4. Carboxylic acid turns into the alcohol. The amide carbonyl just goes to CH2. So this mechanism is kind of a lot, and I really highly doubt that you guys will be asked this much because this is like 4 mechanisms in one. But I'll just go ahead and do it quickly. So for our first step, we have our NaOET, and so that's going to deprotonate an alpha hydrogen. And so you'll notice that they strategically made it so you can't deprotonate this one. So we're going to deprotonate this one right here. So I'm going to draw my little arrow. So anytime in your mechanism you form this this enolate, you do have to show the resonance. So we just show the resonance with our adjacent carbonyl. That carbonyl is going to be an O minus now. We're going to have our enolate anion. Going forward, we can just keep using our carbanion. So we need to form an extra ring. So we can do kind of an intramolecular reaction here. So this this anion can attack our carbonyl on the other ester. So that's going to kick up our oxygen. So in this case, since it's mechanism, we do kind of have to show the mechanism. We can't just kind of breeze through it. So I'm going to actually draw out a bit more here. So we have this. Our other ester is kind of chilling off to the side. And we have our ring. Okay. So now for our next step, we're just going to have that O- come down. It's going to kick out our O-methyl group. All right, so now we've reformed this this dicarbonyl structure, or we formed this dicarbonyl structure. So we can do another equivalent of our NaOET. And since it is a strong base, we are going to deprotonate that alpha hydrogen there. And then for B, we do want to have the non-charged version. So we have to show, actually, I don't know. This mechanism is a little bit confusing, honestly. So they show this this anion structure to show the enolate that is formed from it. But if we wanted to kind of keep going with that mechanism, we have B right here. So now we're, again, this is kind of like a couple mechanisms in one. So now we're going to be doing our decarboxylation. So I'm just going to kind of start here. So for this decarboxylation, the first step is we are going to turn the ester into a carboxylic acid. So that carbonyl gets protonated. A methyl group. So now our H2O can attack at that position. Our ester oxygen is going to steal a hydrogen from the water that we just added. So now our ester is a good leaving group, so we can kick that out. So we're just going to show one of our alcohols. It's going to come back down and form a carbonyl, kick out that, that methanol now. And then we can just have that methanol. I'm going to steal that last little hydrogen. Okay, so now we formed C, this little intermediate C. Yeah, I don't have any room. So for our actual like decarboxylation, what's going to happen is we have this beta keto, not beta keto acid, I guess. I'm gonna draw it like this. So the carbonyl adjacent to this acid can take the proton. That oxygen is going to form a double bond with the carbonyl, and that carbonyl from the carboxylic acid is going to donate its bond back towards the ring. So that's going to remove our carbon dioxide for the decarboxylation part. We are going to have this protonated carbonyl, and now our carboxylic acid is completely gone. And so then for our last step, we would just have a base come in and take that last proton to form our final product. Okay. Yeah. So I did not look at this test. I did not look at the mechanism before I picked this test, so I apologize. This is not gonna be your mechanism, bro. Yeah, this is from 2008, so it's a really old exam. So look at the more recent ones. It's not going to be like this. Like, if it was like this, it would be like half of it. It wouldn't be all of this. From B to C. Like this one right here. Yeah, well, I'm a rebel, so. You just end up redrawing it and then doing it. So I'm just. Like this one down here. Yeah, you do still have to show the enolate anions, the enolate resonance stuff. But I was just kind of lazy. I didn't want to redraw the thing again. So. Also, like, sometimes, like, these older keys are, like, they're graded harder, too. So keep that in mind a little bit, I guess. No. No, this one, like, again, like, if you're asked to do something like this, it would be, like, half of it. Like, this is a really crazy mechanism. I don't know why it's this long. But you might be asked to do, like, the first half where you form, like, where you form B. Or you might start at B and form D or something. Like, you're not going to be asked to do all of this. This is, I don't know. Yeah, like, they hated this class or something. So I'm just going to go ahead and move on to synthesis. So this one is definitely a chapter 19 thing. So this first step, I don't think you guys have learned, but for the most part, the rest of it you guys should have learned by now. This one, we really have to pay attention to the starting materials. It's kind of particular stuff. So just getting started. So we do have this enamine right here. So whenever we have our chapter 19 stuff, enamine versus imine, if you got them on your synthesis, it's like a blessing because it's pretty easy to do your first step. So for enamine and for imine, over the arrow is going to be H+. So we're just going to split kind of between the double bond and that nitrogen. So on our left side, we have this benzene, CH2, CH2, and then we just need to have our amine. And then for the right side, that double bond, so that's going to be the carbonyl part. So I've got the carbonyl is going to be at the position where the nitrogen was attached. So then now I've got this little structure going on. So starting with the left side. So I have this amine. We kind of want to be able to split things up. So amine's not really helpful right now. But what we can do is we can do going backwards, our reducing mechanism. And so remember that whenever we use LaALH4 to form an amine, we're going to have our amide in the previous step. So the nitrogen part kind of just stays the same. The carbonyl would just get reduced to that CH2. So now that I have this carbonyl, I can split this up. So I can do one of my acyl chloride, or it's not an acyl chloride, but yeah, it is an acyl chloride actually. So I can do my carbonyl with my chloride, and then the other side would just be that amine. So I'm just going to have NH2, CH2, CH3. And so you will want to use the acyl chloride and not the carboxylic acid, because acyl chlorides are generally more reactive. I'm not sure like if you get points off, but it's a possibility. So if you're gonna do kind of like something like this, use your acyl chlorides. So then for the acyl chloride, I'm just gonna keep going back on that one. So to form an acyl chloride, I can use my SOCl2. That's gonna bring me back to my carboxylic acid. So ideally, again, I want to be able to split this up. So what I'm trying to do is work it back to an alcohol so I can do a Grignard. So we've got CH2, and then this is going to be CH2, our primary alcohol on the end. So we do have an alcohol here, and we can do a Grignard at this point. We could split it here, or we could split it here and get both of those carbons at once using the Grignard with our epoxide. So left side is going to be my Grignard reagent. Right side is going to be that epoxide, and then we always have our then H3O+. So epoxide, we can just use MCPBA to work it back to our 2-carbon double bond, our ethene. I believe that should be allowed. Oh, it says ethylene oxide, so you could just stop there, actually. So ignore that. And we're allowed to start with bromobenzene, so we just have to do our Mg ether to get our bromobenzene. And so that side's fully done, so that's allowed. This is allowed. For our amine, we're not allowed to start with an amine, unfortunately. Alkenes, alcohols, alkyl halides of 3 carbons or less. So we do kind of still have to work on this one. What we can do is we can do another reducing equivalent. We can turn this back into a nitrile. And from this, we can do a SN2 reaction with our methylbromine and our NaCN. And so we are allowed to start with alkyl halides of 3 carbons or less, so that's good to go. So left side is done. Now I just need to do the carbonyl on the right side. So this one shouldn't be too bad. We can work this back to an alcohol easily just by doing Jones. So we get our CH3, CH2, this can be our alcohol. Then we have our piece over here. Split this, we can just do our Grignard, so then H3O+. Left side is going to be our carbonyl. In this case, since it's on that end, we do want that aldehyde. Right side is going to be our Grignard part. So our Mg, kind of writing it weird, but it's okay. Left side, we want to reduce that back to, or we want to turn that back into an alcohol. So for this one, since we want to stop at that aldehyde, we'll have to use PCC. And then 3 carbon alcohols are allowed, so this one is good to go. And then on that right side, again, we're allowed alkyl halides of 3 carbons or less. So we just need to do our Mg ether to get back to our starting material. Question. Which part? I'm going to zoom back out real quick. Any questions on this one? Or you want me to zoom in or anything like that? Okay. Last part is spec. Yeah, what's up? This one right here? Yeah, so that those will just react together. They don't need something over the arrow. Okay, going to spec. Okay, honestly, guys, spec, please get it down because it does not change for exam 3 or the final. It's like honestly like one of the easier things. So I love spec. This one is tricky. Again, it's 2008, so sorry. So this one gives us a nitrogen, but this is a good practice, I guess, to have. So whenever we have a nitrogen in our formula, it's still going to be the same. So 2 times carbon plus 2 plus nitrogen minus hydrogen all over 2. So if we do this one, so we get 2 times 6 plus 2 plus 1 minus 13 all over 2. So 12 plus 2 plus 1, that's 15 minus 13. So we get 2 over 2, and that gives us an unsat of 1. So unfortunately, we don't have a benzene, but we do only have 6 carbons to work with, so it's not too bad. That one unsat, we see it's in the double bond region. So maybe carbonyl, maybe an imine, very unlikely, or a alkene. So going to my proton NMR. So I'm just going to count my hydrogens real quick, my integration numbers. So I have 6, 7 plus 6. So I do have 13 hydrogens in my proton NMR. So there's not any symmetry. We have all our hydrogens accounted for. So just starting over here on the right, we have a 6H. So that does mean that there is one, I guess there is one symmetrical peak, but like the overall molecule doesn't have a plane of symmetry. So this could either be 2 CH3s or 3 CH2s that are attached to the same thing. Personally, I always go with the 2CH3 theory first because it's more likely just having 3 of the same group versus 2 of the same group. Statistically is more likely. And then we see that this is a doublet. So we're going to have one neighbor. So likely a CH. And then again, like for the 3 CH2 things, it'd be pretty unlikely that we have 3 CH2 CHs and then like one side has nothing. Like it doesn't really make sense. So I'm gonna go with this one. I do have a 1H peak here that's kind of hidden. So I'm just gonna kind of, and it's kind of, it's not really, can't really tell what it is, honestly. So I'm just gonna say it's CH, and then it's got some stuff nearby, but I don't really know what. So I'm just gonna say like M for multiplet. And my last 2 peaks, 3 H's, singlets, so they're not attached to anything. So we have 2 CH3s, most likely, that are not attached to anything. And they are a little bit far downfield to the left. Because they're at 3. So that's pretty deshielded for alkyl peaks. So looking at what I have here, So I have 1, 2, 3, 4, 5 carbons. I'm supposed to have 6. So that means that there's going to be 1 carbon in here that is not accounted for on my proton NMR. So I'm going to say it's going to be a carbonyl. If it was an alkene, we'd have like kind of a couple of really weird peaks going on. And we only have this one right here, but that's not too bad. And also they're not really in the alkene region. They're only at 3. Alkene is about like 5-ish, 5.5. And it's really unlikely that it's going to be an imine. So it kind of makes the most sense that we'd have a carbonyl, and that fits with that one unset that we have. That carbonyl would also get rid of our 1 oxygen, so that's good to go. So I'm just going to put all my pieces down here. So I think I have this carbonyl. I think I have some CH3s that are connected to nothing. I think I have a CH that's got something going on, don't really know what. I have a couple of CH3s that are both connected to a CH. And then I have a nitrogen somewhere. All right. So if my nitrogen is not going to be double bonded, then that means it's going to have to be single bonded to something. So that means it's most likely going to be an amine. There isn't a little peak on the proton NMR. Like for OHs, you might see like a little kind of weird peak that could correspond to an OH or an NH or something. But we don't really have one of those. So I don't think it's going to be, I don't think it's going to have any of its own hydrogens. And so from here, I'm just going to put it all together. So I think that these CH3s are going to be attached to my nitrogen because they're attached to something that either doesn't split or doesn't have any hydrogens. And they are pretty far downfield, so that means they need to be connected to something that's electronegative. So I think I'm going to have this little thing going on. Nitrogen has a lone pair, so that just means we're kind of missing one side. I have these CH3s that are both connected to a CH. So I think these are probably going to be attached to each other. So that means I would have, let me move my stiff. Means I'd have a CH. We've got 2 CH3s attached to it. And then again, we kind of have this one side that's in limbo. And the only peak that's left is that carbonyl peak. So I can just throw that in the middle and I have my structure. So overall, I can just rewrite it real quick. So we had our 2 CH3s that were connected to the same CH. So that's why they gave the same signal. I wouldn't really count on trying to identify the multiplicity of that CH, but it does make sense that it would have kind of a weird large multiplet with 2 CH3s next to it. And then we had our nitrogen. It's very unlikely that it would be double bonded nitrogen. And I don't think it has any hydrogens of its own, just based on the proton NMR that I've seen. And then that would also give a spot for the last 2 CH3s to go. And they were further downfield, so that kind of checks out too. It's almost like a OCH3 or something. It would be a little further downfield. Yes. Yeah, I covered it.
On the P, you guys see that between that 160 to 180, that is considered as like a derivative peak. All of those, the acid chloride, the acid and the amine. So if you notice there's a peak around the 180, that's the acid peak. And secondly, because I noticed with the nitrogen, check your IR. If you don't remember your IR for amine, check back your chapter 12 or 1 note. Basically, if you check your alcohol region, you can tell that there's a 2 peak, 1 peak, or no peak. Then there's no peak, that indicates that it's especially a peak. So keep that in mind.
Any questions on any part of the exam? Okay. Well, see you guys tomorrow. Yes.